Lecture number 14, Q&A. Here we go.
Man, that is a hard question. How do you think abstractly? Well, I don't know the answer to that, but let me give you a couple of thoughts and then we'll see what John thinks. So, first of all, I think computer science is very different than other fields. There's not, in a lot of fields, memorization and pattern matching sort of work, right? You say things like, biologist, you just have to memorize a whole bunch of stuff and just tell me what I taught you. And that's not really, we're in the problem solving business, and every problem is a little bit different. And yes, you learn these basic skills that come to bear. So break out of the habit of trying to sort of remember a solution to your problem, right? That's not really going to work. It's really about taking the parts of the solution and putting them together in a distinct and novel way. So it's more of the, if you will, the raw material, and then you're going to sort of mix it all together in new ways. So break free of the, oh, I've seen this before, I've seen this before. That's number one. Number two, for me, and everybody's a little bit different on this, I don't like to think in front of the computer. Like when I'm thinking about problem solving, I need a piece of paper and pencil, or I need to go for a walk. And just get away from the computer, because once you start coding, you get really bogged down in the, all the little nitty gritty things. You got to make sure that the solution to the problem is clear in your head. And the implementation is separate in some ways for me. In fact, it's very different, because I can think of all kinds of solutions that would take me days, months to implement. So get clear in your head what the problem is and don't worry too much about the underlying implementation. And then the last thing I'll say is it's just practice. The more problems you solve, the better you get at it. So this is your first class. In fact, it's only week 5 of your first class in your first 4 years at Berkeley. I mean, nobody expects you to, like, out of the gate, be solving these problems off the top of your head. So it's sort of a slow process. It'll take time. Next year, you'll be better at it. The year after that, you'll be better at it. And you'll keep getting better at it because you'll keep solving problems and the problems will get bigger and bigger. So be patient.
Yeah, I think that's great advice. Actually, what Hani said reminds me that there's something really different about an online version of 61A from the on-campus version, which is how people approach discussion, where we used to print out the discussion worksheets and everyone would put away their laptops and pull out a pen and kind of start writing down first diagrams and then a description of what they're trying to achieve and eventually code. But code is just one language to describe the process that you're trying to capture, right, in a recursion problem or anything else. You could also describe it in English. You could try to describe it in figures or diagrams. And all of these are helpful because that's how people really think, right, is that they, nobody like thinks in code. We think in, physical metaphors, and we rely on language that we've been learning since we were babies and stuff like that. So yeah, so pulling out a piece of paper isn't as common, I think, now, but it's still a good idea. And going back to the original question of, like, how do you think abstractly, it's that's very broad, but there is a more specific skill relevant to this class and all the computer science classes you might take later, which is to accurately describe the things you have to work with. And then a lot of the problem solving that happens in computer science is, how do I get some new things done with some pieces that I already have available? And the weird thing is that, unlike carpentry, where, like, your set of tools is basically always the same, in computer science, your set of tools is always different. You have, like, a different set of functions that you can call. In recursion, you're kind of like building the tool as you're using it, which is a weird thing. But knowing those things that you can do is really the first step to trying to do anything new with them. And so every function really just has 3 things that you need to know about it. Its domain, so, like, what kinds of things can you call it on? Do you call it on trees? Do you call it on numbers? Do you call it on positive numbers? Do you call it on lists of numbers, whatever? Its range, like what kind of thing will it return, and then its behavior. And its behavior is a concise description of what it does. What's the relationship between the input and the output? And if you can think of a function in terms of those 3 things, then it's much easier to use, because you can check and see, like, oh, can I call this function? Well, if it's a function that takes trees as arguments and I don't have any trees, then I can't call it. And when I do call it, I better call it on a tree, not the tree's label or the tree's branches or something like that. And after I call it, what do I have left? Well, that's the range. And exactly what is this new thing? Oh, it's a tree that's bigger or whatever the function does. So yeah, thinking in terms of those three elements can help you get to know the functions that you have to work with. And then you can reason about like, oh, exactly how do I want to put these pieces together?
I'll add one more piece to that. I like that description a lot, which is that problem solving in coding is not linear. You don't just, start here and end up here and you just take equal steps. It's a very meandering process. Often what happens is you go down this road and you're like, oh crap, I screwed up. This data structure is not right. This abstraction barrier is not right. I need to pull back a little bit and try. So it's a very sort of iterative process. You sort of build a little bit, you realize, we didn't really think through this issue over here. Let's back up a little bit, fix this little thing, go forward a little bit. So it's nobody expects you to start here and end up here and just take a straight shot. So don't worry if there is this sort of back and forth deleting code. It's like writing. I mean, think about writing a 5-page essay. You don't just start at the beginning, at least I don't, and get to the end and be like, done, right? I mean, what do the editors say? The best writers are the ones who know how to delete, right? So I think it's a very sort of iterative, fits and bursts type of thing. So don't get discouraged if you find yourself doing that.
And actually, this relates back to the question in the chat before we started recording, which is like, how often do you correct old code? And I find one of the best ways to debug something is actually just to rewrite it, even if it's my own work. To think like, oh, is there a different way I could have expressed this? And if so, what would it look like in that case? And sometimes it turns out that you find like, oh, this piece that I thought I needed, I don't need because I'm writing it in a different way. And that can clarify the implementation a lot. So, so the strategy of like, start with something and then continue adding to it until it works might succeed for some simple problems, but basically doesn't succeed well for more and more complex problems as you proceed through the course. And instead, like getting rid of everything except for the essence is usually the way to go. The next question was, what is an exclusive OR gate or an XOR gate? And can you build up everything from that?
So I showed you one construction of a circuit that starts with a truth table and says, build a Boolean expression for each of the outputs using only and not. Yeah, that is not the only way you can do it. There are other ways of doing that. What I like about that one is that it's a very sort of methodical process, right? Express the problem, build the truth table, and a not rather, and then or everything together, draw the circuit. It is by no means the only way to do it. It is by no means the optimal way to do it, right? So an XOR is, let's see if I can get this right. It's true if one or the other of the inputs are true, but not if both of them are true, right? So think of the truth table. 0, 0 would be false. Did I get that right, John? XOR?
Yes.
Yeah. 1, 1 is false, and then 1, 0 is true. 0, 1 is true. Yeah. So it's just another Boolean. It's just another Boolean operator, and you can build expressions like that. It's just that the process that I described is a little bit different. Off the top of my head, I don't know how to build an XOR out of transistors, but I'm sure you can. I think it's probably 2 transistors and a resistor or something like that. But I'd have to sort of sketch it out to see it. But yes, you can physically implement an XOR. And there are other types of operators too that are beyond and or not. Those are sort of the building blocks, and then there are these things that go off to the side. But perfectly fine, by the way, and I'm sure, and absolutely, there are in this computer right here, there are XOR gates. Those are very useful. I just described one particularly simple way to design circuits because it led to a very clean formulation without having to do a lot of things. Yeah.
The next question was, what courses cover circuit design? Is it 61C or 16A and B? The circuit design is mostly in 16A and 16B. 61C has an interesting level of abstraction that's between Python and circuits, which is called assembly language. And yeah, the details there are that you need to do more than just describe the relationship between inputs and outputs. You also need to describe, for example, like what to do next, and whether to load something in from memory that was stored before, and whether to store something and where to store it. So these primitives actually also have circuitry associated with them. So if you want to do more than add, but you also want to like manipulate memory and have sequences of instructions and decide, oh, I'm done doing this for a while, I'm going to go do this other function and implement function calls and stuff like that. Well, there's circuits associated with all that and hardware associated with all that. But then you need a language to describe exactly what to do. And then you get a programmable computer. And that language that is implemented not in software, but in circuitry is called an assembly language, which is kind of the lowest level programming language. So that's what you get in 61C. So if you really want kind of the whole stack, 61AB gives you the high level software programming. 61C gives you this very low level, but still software representation of an assembly language. And then 16A, 16B will tell you about the circuits.
And by the way, back in the day, this was before my time, people programmed in assembly language. There were no high-level languages. There was no Python, no C, no Java, none of this stuff. And so people programmed in that, what we would now consider a low-level description. And so you had to know, like, where are the registers stored, and what is the address? And it was incredibly difficult to do. And so we've been creating these abstraction barriers, right? Where now we have this high-level language where we just put in some code, and then it gets compiled down, it gets converted to assembly, and then it interacts with the hardware. So there are several levels still between you and things actually happening on the computer. And you can, I think that sequence is really interesting to sort of see how it all unfolds.
The next question was, if you pass all the tests for the CATS project, but the GUI still doesn't work, should you submit or keep trying to debug it? If you pass all the tests, you might have bugs in your code, but we won't know about them.
Oh.
So in that sense, they won't affect your ability to get credit. It's less interesting to have a program that doesn't seem to work. Now, it's hard to tell whether when the GUI doesn't work, that's because there's some issue with your code, or whether there's some issue with our code because we provided the GUI. It seems to have worked pretty robustly in the past, but I'm not sure. Yeah, I didn't teach this course over the summer. They always make changes. Maybe they broke something. And then it might be that actually that there's a configuration issue with your computer that we didn't anticipate. Or yeah, so like the way in which it connects to the server or something like that is hard to get around. Yeah, so we have had students in the past that have like particular antivirus software that interrupts the multiplayer server or something like that. Yeah, if I had to guess, probably if you're passing all the tests, then the problem is not with your code. But I can't guarantee that's the case, but that's probably what's going on. And will we debug it? Hopefully. Yeah, so there's definitely stuff that we don't check for that is important. And this is true of any test suite, is that it's basically impossible to prove that a program does what it's supposed to do if that program is just written in Python with no constraints. There's an interesting branch of computer science called verification that is about making sure that you can prove that your program really does what it's supposed to do. But the trick there is that you have to express what it's supposed to do in language that the computer can understand. And then you also tend to have some restrictions on how you write your program to make it easier to verify. So these techniques still aren't used very often in practice, except for with very low level programming, like making sure that a circuit board does what it's supposed to do. So anyway, yeah, it might be the case that there are some issues that we didn't detect, but you could certainly just submit your project and not worry about that. So yeah, the question was about like, how do you approach add trees, which takes in two trees and returns a new tree where each corresponding node from the first tree is added with a node from the second tree. If a node at any particular position is present in one tree but not the other, it should be present in the new tree as well. So you could kind of pretend that a tree that's missing some branches relative to the other tree just has zeros everywhere, I think is one way to think about it. And apparently this is a lot harder than previous tree problems. That's exciting. Well, let's do it anyway.
An ominous warning.
So let me just try to get set up here. Add trees. I think since these are both trees, they both must have a label. They might have different lists of branches, but they both must have a label. So we can guess at what's the label of the final thing that we want to build, which is that the result label is the result of adding together the label of T1 and the label of T2. And I always like say in words what I'm trying to do to a tree before I start trying to program, because that helps me make sure that I'm kind of combining the right types of values. So you can't add two trees together. If you do, you won't get an error, but you will get the wrong thing. So instead, you want to get the labels and add those together. Now, what about all the elements? I'm not going to use this built-in zip function because that seems like it's more complicated. We could try that later if you want. But I think we want to go through and for each corresponding pair of branches, we want to add those branches together, and then we'll get new branches. So yeah, so maybe we'll start with no branches, and I think it would be helpful to have an index of which branch I'm on, and then I want to go through all the branches that exist in both trees. So one way to do that is to say, well, I is less than the len of the branches of T1, and I is less than the len of the branches of T2. We might think of a more concise way to say that later, but this is a fine way to say, I want to go through all the i's where they exist in T1 and they exist in T2. And what will we get? We'd get a new branch that is the result of adding together branches T1I with branches T2I. I'm doing this in kind of the most explicit way possible. Now, what does it mean to add these two things together? Well, we actually need to like add their labels and add all of the elements in the rest of them. Fortunately, we have a function that does that. It's called add trees. So to make this fit on the screen, I would call this B1 and B2 maybe. And then we'll just call add trees on B1 and B2. What do we do with the new branch? We'll learn in Friday's lecture that there's other ways to do it, but one way is just to redefine result branches, to have all the branches that were in there before, plus there's a new branch. So we'll build a list containing just that branch and add that in. So that will give me a longer list that's got all the elements of this plus one new element, which is this new branch. Now we have a bunch of branches. And if we had some guarantee that T1 and T2 had the same structure, then we'd be done, I'd say. But being done means we'd need to return a tree. That's what add trees does. So we'd call this on result label and result branches. The tricky part is that maybe it was the case that I didn't capture all the branches in T1 because there were fewer branches in T2 or something like that. So what do you do about that? I think that any branch that's in one but not the other doesn't really need to be added to anything. It just needs to be included in the result. So which ones did we leave out? We left out, I think, all the branches of T1 from I onwards. So let's just kind of check with an example. If this had 4 branches and this had 2 branches, then after you do this iteration, I will be equal to 2, and we'll reach here. And if T1 had 4 branches, then we do want branch 2 and branch 3, which is exactly what will be captured by this slicing expression. So we could write something like that. And what if it was the case that there were more branches in T2 than there were in T1, well, then we need to put those in the result. Something like that might work.
The question to ask yourself is, why are both of them there if only one of those can be true, right? You can either have extra in T1 or T2. So why are we allowing both of those in there?
Yeah, there's the implementation again, if you want to think about that. And I think I'll just quickly check and see if this works, except I'm not sure that I have print tree defined anywhere. Might have to grab that. Yeah, I gotta get print tree. Where's print tree? Oh, it's in there somewhere. There you are, print tree. We'll put that in my file of important functions related to trees. I can try this all again. What am I trying again? I want to run these. Ooh, runs forever.
That's not good.
Let's see why that is.
Oh, you're not incrementing I, John, in the while loop.
Rookie mistake. Okay, now it works. So, I mean, there's lots of ways to clean this up. We could, for example, have this like be a minimum of these two values. We got it slightly better.
Forgot the colon.
We could have given names to branches T1 and branches T2, because it seems like we call that just a ton of times, and it might just simplify things if we'd given them names. We could have replaced this while statement with a for statement. The whole story about zip, I think we could talk about really quick. So what zip does, if you give it two lists, is give you a way of iterating over both of those lists kind of concurrently. So the 1 and the 7 go together, and the 2 and the 8 go together, and the 3 and the 9 go together. The nice thing is that if you zip lists of different lengths, then it just kind of works its way up until you get to the part that you want. So right, so instead of all of this, we could have gone through B1 and B2 and the result of zipping together the branches of T1 and the branches of T2. And we'd end up getting rid of that line. Now we've kind of lost track of our notion of I, and that can be worrisome, but we could reconstruct it actually. So I could be just the len of the result branches, and then this would probably work. Yeah, it looks pretty good. And yeah, finally, could you somehow like get this into one line? And usually it's the case that if you ever start with a list and then you are adding just one element at a time to that list, you could instead write it as a list comprehension. So this could have been add trees B1, B2. We're going to have to give it some shorter name for B1, B2 in this zip. Well, still doesn't fit. How disappointing. We'll make it fit. Okay, so those are the result branches. Now I'm just fiddling around, but whatever. You probably get the idea. And then you can delete all this stuff.
There's a great line by, I think it was one of the guys who wrote C in Unix, and he said, debugging is twice as hard as writing code. So if you're as clever as you can be when you write code, you will by definition not be able to debug your code.
Yeah.
So, and I mentioned this because John did something really nice here. He wrote code that was not particularly elegant. Sorry, John. A little bit longer than you might want, but it was very logical. You could see what he was doing in every step. He got that to work. We make sure, and now you can go back and start tightening it up and cleaning it up and making it more elegant if you want to. But sometimes that slightly longer code, slightly more explicit, is actually preferred because it's a little bit easier to deal with. I'm like, if I looked at this, I'd have a hard time parsing this code, whereas the previous code was, you could see what was going on. It was good.
Yeah, I was just trying to show there's kind of different ways of solving the problem, and there was this hint about zip, so I figured I'd tell you what it was. You know, zip is an abstraction that most Python programmers really get used to because it shows up a lot that you want to like pair things together in this way. But if you're unfamiliar with it, then this looks completely confusing. So it just like takes a while to get used to or familiar with this notion that you would take, you know, the first elements and pair them together, and the second elements and pair them together, and the third elements to get them together. Once you're used to that notion because you've seen it a dozen times, then this idea of like, oh, call add trees on all the corresponding pairs is easy to read. But at the beginning, if you've never seen the term zip before, then it's really hard to read. So kind of depending on your comfort level and the comfort level of whoever might read your code, it can make a lot more sense to kind of write things out explicitly. Or, you know, if you've all been programming together in Python for years in your community, then you could write it this way because zip is kind of a common verb in that community, and it's not necessarily confusing.
And this works for assignments too. I mean, we may tie your hands and say you have to use zip. But that doesn't mean your first implementation has to do it. Just figure out how it works, and then you can back your way into the constraints. And that sort of helps you think about, you know, how are we solving the problem without one hand tied behind your back if you're not comfortable with a particular concept, but at least you have it working at that point.
And it's worth noting that a lot of expressions that existed in the other implementation still exist here. Like we didn't actually have to change this code as long as we kind of captured what was going on. So that's generally true, is that there's lots of different ways to write the same thing, but they often share the same elements. A follow-up question was whether you could write the same implementation just using recursion. Yeah, great question. So we are using recursion already in the sense that we're calling add trees within the body of add trees. There's one part that we're not doing recursively, which is that we're iterating over the branches. So this is kind of a mixture of iteration and recursion. Could we make that part recursive too? The answer is yes, but we'd basically just write a helper function that does this process of building up the result branches. We just build it up recursively. So it's actually not so bad. What do we need? We need the branches of 1 and the branches of 2. We pass those in. Or actually, let's just stay consistent. We'll pass in T1 and T2. And if it's the case that one of these is empty, then there are no branches in the result. Otherwise, we're going to have to construct the like first add tree and then add that on to the rest. So the first thing I think would be the result of calling add trees on branches T1, 0. Almost got it right. And branches T1, T2, 0. And then what do we do with that? Okay, I'm going to move this in just so it fits. We want a list that has that as its first element, and then the result of build result branches on, oh, I guess we do need lists of branches here. So here, BS1 and BS2 are the branches of two trees, are the remaining branches of trees. Well, we'll leave it like that. So we're getting close. And see, there is like a fair amount of iteration here to get it right. That's not right. And that's not right. And that's right. Maybe. And then we just need to kind of forget about the first element of both of these. Make it fit. And then we get rid of this expression and replace it with a call to the helper function that we built. And perhaps we've then built something that works. We did not build something that works.
John, I don't want to put pressure on you, but you got 3 minutes.
Okay, so now it works. Yeah, so if you really want to take some iteration and turn it into a recursion, there's always a way. Here's one possible way. This would be done rarely in practice, I think. If you just are going through a sequence of something, then use a list comprehension or a for statement or a while statement or something like that. Recursion is really wonderful for recursively processing trees. So the add trees here is really an important recursive call. That's the reason we learned recursion. And this is just kind of an exercise in knowing that it's possible. The student then suggested that instead of returning an empty list in the base case, you return the rest of the other tree. Fine idea.
Yeah, although now you have to know which one is, you can't just do the min though.
Yeah, it might work. There you go. Good idea.
Yeah. Right, that saves some effort.
Okay. We added a lot of trees. Thanks, folks.
Thanks, guys. See you Friday.